Hello kids, today we are going to talk about the properties of a substance that are affected by the types of intermolecular forces they experience. So first I will explain what those properties are and why they are affected by the types of intermolecular forces they experience. And then the second thing is I will go over the unique properties of water that make it so cool and interesting. So the first property that we're going to talk about that is affected by intermolecular forces is the boiling point of a liquid. So if our substance is a liquid, when it boils, the boiling point is the temperature at which those molecules escape from the collection of liquid into the gas phase. So you can imagine that if this collection of liquid molecules are holding on to each other tightly, it would require more energy for one of them to escape into the gas phase because they would have to break that intermolecular attraction to be able to get away from the liquid into the gas phase. So what that means is that the stronger the intermolecular forces are between the molecules of liquid, the higher the boiling point is going to be. It would require more or higher temperatures, more energy to separate these liquids from each other, these liquid molecules, so that they can escape into the gas phase. And going hand in hand with that are evaporation rates. So evaporation rate is how quickly a liquid evaporates. So instead of the temperature at which it starts to evaporate, it's how fast that happens. And evaporation rate will be affected by intermolecular forces in the same way. The stronger the intermolecular forces, the slower the evaporation rate. All right, another property that is affected by intermolecular forces is freezing point. So the freezing point of a liquid is the temperature at which that liquid will start to organize into a solid. So these molecules right here are in the liquid phase, and they're, just kind of unorganized. And then as you reduce the temperature, they start to get more ordered and form crystal patterns as a solid. And the temperature at which that happens is freezing point. So if you think about intermolecular forces and their role in the freezing point of a liquid, the more attracted molecules are to one another, the easier it will be for them to start to order themselves into this nice crystal pattern. So the stronger the intermolecular forces, the higher the freezing points. And the weaker the intermolecular forces, the lower the freezing point. So an example that I can give you is carbon dioxide versus water. Water has a freezing point of 0 degrees Celsius, whereas carbon dioxide is negative 78 degrees Celsius. So carbon dioxide is so nonpolar, its intermolecular forces are so weak that you have to lower it to a really, really cold temperature before they'll start to organize themselves into a solid. And of course, going hand in hand with freezing point, you would have melting point. So the melting point of a solid into a liquid, the stronger the intermolecular forces of attraction, the higher the melting point. It would be harder to get them to want to separate from the solid phase into the liquid phase. So stronger intermolecular forces lead to higher melting points. Surface tension is another property that's affected by intermolecular forces. So surface tension is due to the fact that the molecules, so let's look at the molecules that are below the surface of a liquid. So this is a molecule and this is a molecule below the surface of the liquid. And if they are attracted to one another, then this force of attraction between the same kinds of molecules is called cohesion. So you have cohesive forces that are acting in all directions from the other molecules in this liquid or on this molecule right here. And same is true here. So essentially what you have are a whole bunch of molecules that are surrounding this molecule, and they're all pulling on each other because of their intermolecular forces, because of this cohesion. At the surface of a liquid, you have the same thing. All the liquid particles that are beneath the one that's at the top here are pulling, or they have interaction with one another, intermolecular forces, but none up here because there's no liquids up there. So that creates this sort of film on the top of a liquid that creates, or that is, your surface tension. So surface tension is basically how strongly the molecules at the surface of a liquid pull on each other. So liquids with strong intermolecular forces would have higher surface tension. So when you pour a liquid from a bottle or a flask or something, when you pour it, some liquids pour very smoothly, and that's because they have really high surface tension. So like this right here is a liquid that has pretty high surface tension. The molecules are sticking together and it's pouring really smoothly, whereas this is really choppy, and when you pour it, it's kind of hard. I don't know if you've ever tried to pour rubbing alcohol or acetone into a cup, but it splatters everywhere. It doesn't make a nice stream. That's because it has very low surface tension, because its molecules aren't very attracted to each other, and so it doesn't make this nice pour. Right, another property that would be affected by intermolecular forces between the molecules is viscosity. And viscosity is the fluid's resistance to flow. And of course, that also has to do with surface tension. But viscosity, if you look at these liquids right here, the more viscous they are, the more resistance to flow they have. And so this would be a really viscous liquid because it's just not even pouring, whereas this would be the least viscous liquid because it's pouring, but it's really choppy. And of course, you range in between. This is probably water, so it's viscous enough that you can pour and get a nice flow, but not so viscous that it won't pour. And this is probably something like honey. Honey's pretty viscous. It's really thick and it resists its pouring. So what causes a fluid to resist flowing? Well, in a flowing liquid, the molecules are trying to get past one another. And so if you have a whole bunch of molecules and they're trying to flow past one another out of the tube, the stronger the intermolecular force is, the harder it is for them to get past each other. And so they're going to be more viscous. So the last property that we're going to talk about that's affected by intermolecular forces is this ability of something to dissolve something else. So right here I have a picture of kind of what happens when something dissolves. So you've got your solid and all the particles that are stuck together, and then your liquid surrounding it. And then what happens are the liquid particles come in and just separate the solid particles from each other, and then just kind of pull them away into solution. And in order for something to be able to dissolve something else, it needs to be attracted to it and want to surround it and take it away into the solution. So you can imagine there has to be some sort of force of attraction between what we call the solvent, the thing doing the dissolving, and the solute, which is the thing that's getting dissolved. There has to be an attraction between those two particles for the solute to dissolve into the solvent. So that leads to this like dissolves like phrase that you're going to hear. And what that means is that polar things dissolve polar things, and nonpolar things dissolve nonpolar things. So for example, oil is a very nonpolar substance, and if you want to dissolve oil, you wouldn't use something polar because it wouldn't be attracted to that polar molecule. So if you want to dissolve something that's nonpolar, you want to use something else that's nonpolar. So if you want to get soap out of something, if you want to get oil out of something, you would not use water. You would use either water with soap in it, because the soap will add a certain non-polarity to help pull the oil out of your clothing, or you can use a non-polar solvent like acetone. That would work. And going hand in hand with dissolving is something called miscibility. Miscibility. Miscibility is how well two liquids will mix, so how well and how evenly they will mix. So again, I can use oil and water as my example. Oil and water are not miscible. They don't mix well or even evenly with each other. When you try to mix them, because of their different polarities, they just separate. All right, let's talk about the unique properties that water has. So water's properties and what makes it so unique are due to the fact that water is an extremely polar molecule. So the oxygen has a slightly negative and the hydrogen's a slightly positive charge. And it's such a big difference in charge that makes that a really polar molecule. And so water will experience hydrogen bonding, the strongest intermolecular force, with other water molecules. And since water is 65% of your bodies and 70% of the earth is covered by water, and most living things rely on water in some way, water is extremely important, and its unique properties are part of why it is the basis of life. Water has an extremely high boiling point, or not extremely high, but a relatively high boiling point. So if you look at the other elements in the same family as oxygen that form similar compounds, their boiling points are all extremely low. Look at them. I mean, they're -4, -42, and -62. And then water is way up there at 100 degrees Celsius. So water's high boiling point, because of its strong hydrogen bonding, makes it so that creatures can live in, that have water is in their bodies, can live in extremely hot temperatures without having to worry about their fluids evaporating or boiling. And at the same time, it's got a very low relative freezing point. So again, if you look at the ranges here between hydrogen sulfide, look how little that range is, but water has this giant range between where it boils and where it freezes. And that's in part due to its hydrogen bonding. So again, living creatures can live in a wide range of temperatures and not have to worry about their tissues freezing and them getting frostbite, or the water in their tissues boiling and them dehydrating. Water's strong intermolecular forces, or its hydrogen bonding, is also responsible for the fact that it's really good at adhesion and cohesion. So adhesion is when a molecule of one substance is really good at sticking to a molecule of another substance. So for example, a paper towel. Water is extremely good at soaking into a paper towel. And the reason why is because it's adhering to the molecules in the paper towel. Cohesion is when two molecules of the same substance are really good at sticking together. So water is really good at sticking with other water molecules, which is why when one water molecule adheres to the paper towel molecules, it climbs up and takes other water with it. So that's why this paper towel can soak up water, because of both adhesion to the paper towel and cohesion of adjacent water molecules. It's the same reason why water will climb up thin tubes really easily. So straws, for example, if you put a straw in water and you look at it, you'll see that a little bit of water has climbed up inside of the straw all on its own. And that's due to, again, adhesion of water to the sides of the straw and the cohesion of the water molecules to each other. This adhesion and cohesion make it possible for trees to get water from their roots to their leaves. The water molecules are capable of adhering to the sides of the xylem and phloem in the tree trunk, and then cohering with other water molecules. So as they climb up the sides of the little tubes inside the tree trunk, they also pull other water molecules with them. It's also the same reason that when you're measuring water in a graduated cylinder, you get that curve that's called a meniscus. It's because of adhesion and cohesion of water molecules. Water also has really high surface tension. And what that means is that water pulls in on itself. and makes a thin film on the top of like, say, a glass or a bead of water. So water molecules are capable of pulling in and cohering to each other and making these little sort of droplets, like, for example, on your car surface after you wash a car. They're also it's really hard to break that surface tension. So you can see the swimmer is kind of coming up out of the water, and the water is sort of coating that swimmer, and that's because of that strong surface tension on the top of the water. Surface tension is also responsible for the fact that small bugs can just walk right on top of water because they're not breaking those intermolecular forces. They're able to actually just walk on the surface of that water. And it's also the reason why belly flops hurt. Water also happens to be pretty viscous when compared to other molecules of similar structure. So it resists pouring, so it has a nice smooth stream when you compare it to other molecules of the same or of similar structure. Water is extremely unique in that when you freeze it, its density is lower. So it's got a smaller or a lower density when it's solid than it does when it's a liquid, which is really unusual because for most substances, when you get it cold, its molecules slow down and actually get closer together, which would make the density go up. Not for water. Water's density actually decreases when it freezes. So when water freezes, its molecules actually set up into this sort of hexagon or honeycomb pattern. And that six-sided hexagon happens to be less dense than water in its liquid form. And that makes ice cubes float instead of sink on top of liquid water. It's also responsible for why icebergs float instead of sink in the ocean. And that honeycomb structure is actually the reason why snowflakes are always six-sided, because all of the crystals in a snowflake are six molecules of water, 1, 2, 3, 4, 5, 6 molecules of water forming little honeycomb crystals or six-sided crystals. And lastly, water is the universal solvent. That essentially means that it can dissolve a lot of other substances. So it's capable of dissolving a lot of other polar substances and, of course, ionic substances as well. Due to the strong polarity on a water molecule, it's slightly positive end or slightly negative end on the oxygen, and its slightly positive end, because the difference between those two is so great. It's really, really polar, and so it's capable of attracting and dissolving lots and lots of things. So that brings us to the end of my presentation, or this presentation, on properties affected by intermolecular forces.